Hello everyone. Today here in this video, we would like to solve a problem basing on the concept of simple pendulum. Let me read out the problem for you first. What is the effective time period of a simple pendulum when the bob is immersed in liquid of density x? So I will explain what's the meaning of the problem it is. First of all, a simple pendulum is somebody where there is a fixed rigid support to which there is a light and extensible string is attached. At the bottom of that, a heavy point-sized mass is suspended, whose mass is equal to m. On this, therefore, when acceleration due to gravity, force, weight, mg is acting. In that case, when it is slightly disturbed, it makes oscillations. To make one oscillation, complete oscillation, it takes some time. Time taken to complete that oscillation is called time period. Formula for that is 2 pi into root of L by G. This we have already derived. This is all when this pendulum bob is in air, where no upthrust is considered. We assume it like a vacuum in the other sense. Now he is saying this bob is no more in the air, but it is immersed in a liquid. Whenever there is a liquid on the bob, there is not only the weight acting, there is an upward force to the liquid called thrust acting. So the resultant force is different. So time period also will be different. We want to derive an expression for that. So, so what I would like to discuss now is when immer- what happens to the resultant force on the bob is the point I want to talk. Of course, its weight always acts in downward direction, and as it is immersed in the liquid, as I told you earlier, there is a force called upthrust. Upthrust always acts in a upward direction. We'll be talking about that in the fluid dynamics, fluid statics chapter. Well, so the resultant force will be still in a downward direction, but that is little less than the weight because there is an upward force. So I can write F resultant as weight minus upthrust. Weight is in downward direction, upthrust is in upward direction. As weight is dominating, F resultant is also in a downward direction. So how much is that F resultant is? Let us try to calculate. Yeah, F resultant is mass into acceleration, this value. Weight is equal to mg minus upthrust. We have a formula for the upthrust. The volume of the fluid displaced, density of the fluid into gravity. What do you mean by volume of the fluid displaced? Let me try to explain. Yeah, as there is a spherical bob, and when you place it in a fluid, this spherical bob, to occupy its space, has to push away some fluid. So some fluid is displaced. That's called volume of the fluid displaced. Density of the fluid, let's assume like dF, and G is the gravity. So in the place of a thrust, I can write volume of the fluid displaced, density of the fluid, and acceleration due to gravity. But be careful here, as the bob is completely immersed in the fluid, how much of the fluid is displaced is equal to the volume of the bob itself. So what we can say, as bob is completely immersed, volume of the fluid displaced equal to volume of the body itself. That implies mass into acceleration on this bob is equal to weight minus, in the place of volume of the fluid, I can write volume of the body, density of the fluid into that. Mass of this bob can be written like, the definition of a density as mass by volume. So mass can be density into volume. So mass can be density of the body into volume of the body of acceleration equal to, again in the place of mass, density of the body, volume of the body, acceleration. Minus volume of the body because volume is completely immersed. So in all of them, density of the body is common. Sorry, volume of the body is common, so that can be cancelled. So density of the body into acceleration is density of the body minus density of the fluid. Mass equal to volume into density. Of course, into G here, so acceleration is G. So acceleration experienced by Bob when he is immersed in the fluid is density of the body minus density of the fluid by density of the body into G. Or if I divide with density of the body, 1 minus density of the fluid by density of the body into G. Density of the body, let me just, by density of the fluid is called relative density. Generally, relative density with respect to water is told, but here this is the relative density of with respect to this fluid. It is given in the problem that relative density of that fluid is equal to x. So I can call this value as x. That implies acceleration becomes 1 minus. See, be careful. This is body by fluid, but you got fluid by body. So the reverse of that relative density has to be taken into G. So this is the new acceleration. With respect to that, I will get a new time period as of a simple pendulum is 2 pi into root of L by not just G, L by A, because it is now immersed in a fluid as it is being told here. So 2 pi into root of L by, in the place of acceleration, I can write 1 minus 1 by relative density into G. This is how a new time period has to be calculated, right? So it is something less than G because G minus something is there. So as it is something less than G, denominator is less, so the time period will be more. So we are going to get a different time period in this case when compared with the earlier case of simple pendulum in iron. That's it. Thank you for watching.